Okay, so we're going to solve an example of a Castigliano's theorem using find the deflection of a structure using the Castigliano's theorem. So let's say I have this structure here that is tied to the wall, and I'm going to have a force affecting my point B here. So I'm going to label some of the points. This would be B, this would be A, and O. Center O. I have those dimensions, and I also know that the diameter of this rod would be 1/2 of an inch. Okay, this is going to be subjected to a force here at B that is located at an angle. So this little triangle that I drew here would be 4 and 3, and obviously the hypotenuse would be 5, and that's what we would use to have the components, to find the components of F in both X and Y. So my force F would be equal to 15 pounds force, but I know that I know that there's going to be a component in the X direction and the Y direction. So let's also do the axis. The axes would be X, this direction, Z, this direction, and the vertical one would be Y. Okay, and what I want to find is the deflection at point B in the direction of the force. In the direction of F. Okay, and that's exactly what the Castigliano's theorem allows me to calculate. So I already know that what I'm going to get from this is dB is equal to the partial derivative of the energy in the direction of the force with respect to the force, and that's going to give me the deflection in the direction of the force. Okay. All right, so what we're going to find out is that because of this force, there's going to be torques and moments and even shear. We're not going to take into account the shear. As I explained, that's usually very, very small compared to all the other stresses due to on rods this long. And what we're going to do is moments, torsions, and compression and tension forces, right? And so the first thing that I need to do here is find an expression for U, and to do that I'm going to need to find out all of the external loads in both of the elements of this structure. So the first thing I can do is do a drawing for OA and see what that is subjected to. So I would have A here. I would still have the same axes, sorry. So X, Y, and Z. And I can translate this force to where it is located. So there is going to be a component going down, right? And because of the components that I gave that I showed here for the X and the Z, or the X and the Y direction, I know that F of Y, the Y direction would be 4 adjacent over hypotenuse 5 of F, which is 0.8 of F. And for X, it would be the opposite 3 over hypotenuse 5, 3 over 5 of F, or 0.6 F. Okay, so I'm going to use those. So what I know from that is that there's going to be an F of X and a F of Y, so 0.F going down and 0.6 F going to the positive X direction. Okay, so I already have those. I know that this 0.8 F is going to cause bending, and the 0.6 F is going to cause tension. So I can write those for for this rod OA, I'm going to have tension. So for my equation of sigma equals P over A, I label those as P. So my force P is going to be 0.6 F, and there is going to be a moment that depends on the x-axis. So the farther away I am from this 0.8 force, the higher the moment is, and it's going to be highest here. Okay, so that moment that is a function of x, okay, and that will affect this, or like if I'm gonna just draw it, it would be over here. It's gonna be a moment sub z. Okay, this rod is gonna try to bend downward because of this force, so it's generating this moment. So mz of x is equal to 0.8 f times whatever distance I move away from this point in the x direction. Okay, 0.fx. Okay, but also because of those forces, because those forces are not actually located here, but they're actually located at B. Okay, so there is going to be a torsion. If I multiply this 7 inches times the vertical component of F, AO is going to experience some torsion in this direction. So basically what I just said is that because this 0.8 F right here is not located here, but at 7 inches away from it, it's going to generate a torque. So I'm going to write that down about the x-axis. Okay, torque. So I have T equals to that force 0.8 F times the distance of 7 inches. Okay, so basically 5.6 F. Okay, and this is not going to be dependent on any dimension variable. So it's not a function of x like mz. The torsion is the same throughout the rod OA. Okay, it's always going to be 7 times 0.8 F. Okay, so that's constant. And then the last one is because this component of the force in x is also at 7 inches, there's going to be a moment about the y-axis. Okay, so if my y-axis was here, and I'm replacing this component of the force in the x direction, this force times 7 inches is causing a moment in this direction. Okay, so it's going to be labeled my because it's about the y-axis. So it would be here, my. Okay, and it would have a value m sub y would have a value of 0.6 f times that 7 inches from before. So basically 4.2 f. And again, it's not a function of x or y or z. It's the same moment throughout the whole rod OA. Okay, so the only one that is a function of a variable here is m of z, which is a function of x. As I move inside the rod OA, the values of mz are going to be changing. Okay, so I already have those, and I don't have anything else affecting. I have a torque, I have an mz and my, and some forces, okay, that cause also bending and tension in this case. Okay, so now I'm going to do the drawing for AB. Okay, so for AB, where this is B and A, I'm going to have the same forces, obviously. So there's going to be a component here, 0.8 F and 0.6 F in the X direction, Z direction, and Y direction. Okay. Now, as I move away from B towards A, I'm gonna find that the moment about x increases. Okay, so the moment, there is gonna be a moment about x. I'll write that down. Moment about x, sorry, that is a function of z. Okay, the moment at b, here at b, it would be 0. But as I move away from b, there is a distance that multiplied by 0.8, a distance z times 0.8f that is causing this moment m sub x. M sub x, right? And so that is defined as 0.8f times z, of course a function of z, right? There is no compression or tension in this case because both of these forces, 0.8 and 0.6f, are parallel to this surface, so there's no compression. But there is one more moment, which would be about the y-axis. So again, as I move away from b towards a, there's going to be a distance that multiplied by 0.6f, this vector, times this distance z, would give me a moment my. M sub y, not m times y. Okay. And so what I just said is m sub y of z as a function of z would be 0.6f times z, right? Now I know that to use my Castigliano's theorem, I'm gonna have to have all the u's, the energy expressions for all of the different types of deformation, but also because of how they're written as an integral, and I'm going to have a partial derivative with respect to f, I'm going to need the partial derivative of those loads with respect to f. So I have all of these loads, but I'm also going to need, for example, dp df and dmz df and dt df and dmy df, and the last two, dmx df and dmy df. Now they might look, it's not working, they might look the same, this my and my, but this one is for OA, so basically there is a difference between these, because this is for BA and this is for OA, so they're still different, okay? And so these partial derivatives are super easy to calculate. So this would be with respect to f, 0.6, with respect to f, 0.8x, with respect to f, 5.6, with respect to f, 4.2, and these two would be 0.8z, so I'm deriving it with respect to f, and 0.6z, right? Why do I need all of those? Because, for example, I'm just going to write the first term here. If I only wanted to see the deflection in B due to, for example, this first load, 0.6 fp, I would write something like the partial derivative with respect to f of the integral of p squared over 2ae dx. Okay, because this is my expression for the energy due to a compressive or tensile force. Okay, so if that is the energy, if I derive it with respect to f, I would get the deflection. So basically, if I'm already doing the partial derivative, this would be not u, but the deflection. Okay, but only due to this force. So I'm gonna have that plus the one due to this moment z, torque, this moment y, this moment x, this moment y. And that's exactly what I'm going to do here with Castigliano's theorem. So let's keep going, and I'm going to write that expression of what I just said. So I have all of these forces, and basically my my delta b, the deflection that I want to find, is going to be the partial derivative of with respect to f of the integral of p squared over 2ae dx from 0, from this 0 to a, from O to A. All of these are going to be affecting O to A, all of these four. And that distance is going to be 15 inches. Okay. So from 0 to 15 inches. And so notice, I'm going to do it here, plus the next one, plus the next one, plus the next one. And I have 6 of these. Okay. I do it for all 6 of these. But this first expression, I can do the derivative. I explained this in class. I can do a partial derivative of this inside the integral. So the partial derivative of p squared is going to be 2p times chain rule dp df. Okay, and divided by what I already had in there. Integral dx 0 to 15. Okay, so basically I can skip. I will have for the next one. So for mz, I would have something like from 0 to 15 again, because it's affecting OA, and that's a length of 15, m squared over 2ie dx. Okay, and so when I do the partial derivative with respect to f of m squared, this would be 2m, and chain rule the internal derivative dm df. Okay, over what I already had here, and same integral with same limit. And so this is the reason I needed this dm df and dp df. That's why I calculated all of these here before. So I'm going to have dm df, dp df, dt df. I need all of those in these equations. Okay, so in this case that would be m sub z, and dm sub z df, right? And so I'm going to list all the 6 that we're going to work with. So the next one would be due to torsion. Torsion would be t squared dx over 2jg, and then the derivative of that would be 2t dt df over 2jg. Same integral, same limit with respect to dx. Obviously these 2's are going to go away, so 2 and 2, 2 and 2, right? And as you're probably noticing, so I already had the load P written here as 6F. I can substitute that, and I will do it for one of the integrals, but just so that you know where we're going with this. And the dpdf as 0.6. So I would only be substituting this P right here and this dpdf. Okay, A and E and I and J, I'm gonna need all of those, but the important part here, or like the harder part of this problem, would be to identify those. So that's why we did it at the beginning. So because of what I just said, it's also important to calculate the other information. So I'm gonna need the area. So let's do that. The area is equal to pi d squared over 4 pi times 1/2 squared over 4, and this would be equal to 3.068 times 10 to the minus 3 inches to the okay, sorry, never mind. This number is not this. This would just be whatever. This in inches. We're not gonna do a whole numerical value here anyways. This would be inches squared. And then I can do pi over 64 d to the 4th. So pi 1 over 2 to the 4th over 64 inches to the fourth. J would be twice I, whatever number I got, times 2. And I think that's it, because then there's just the properties of the material. So let's say J and E are given. Okay, so going back to these integrals. So I have these 3 expressions for the 3 first ones. Let's do the fourth one. Would be d df, the integral of another moment. So I know that this is going to end up as this term. It would be m sub y dmy df over IE, and the integral from 0 to 15 dx. Okay, and then the last two are not from OA here, OA, but from AB. So my integral will be from 0 to 7, because that's the length of AB, and it's due to these 2 loads, so mx and my. So mx would be a partial derivative. Again, it's going to end up looking like this, so I'm going to skip that intermediate step. Due to mx, I would have 0 to 7 m sub x dm sub x df over IE, and in this case is with respect to z. I'm doing the integral from a to b, which I know is 0 to 7 in the z direction. Okay, so that's a dz. Right? And so the last one I have here is due to my. I already did mx, now my. So my is working 0 to 7 my dmy df over IE and dz. Okay, and so basically what I'm saying is that if we add all of these terms, I'm going to find the deformation of B, the deflection of B in the direction of the force. So notice that there's going to be 2 forces, one going down and one going in the positive x direction. I'm going to end up with B moving towards somewhere in between. And actually, it's not necessarily due to these loads, because like I said, there's torsion, so this is going to have an angle of twist, and then times this distance, it's going to go down. So Castigliano theorem already encompasses all of that information, right? So let's work on some of these integrals. And let's do it so that we can still see the values of the forces. So I'm going to do the first one. The first one is pretty simple. I have 0.6 F and the PDF is 0.6. So when I go here, I find that this is the integral from 0 to 15 of 0.6 F times 0.6 over whatever area I found and whatever E I was given, okay, dx. And so I have the force and I have the 0.6. Now I want to explain this and why we got this derivative. We could have said that this, like I explained in class, that this force P is constant. The force P affecting that stretching due to the tension here is constant throughout the x-axis. So I could easily have used not the integral version of the deflection, as Castigliano's theorem proposes, but I could just use PL over AE. Okay, so basically what I'm saying is I could have just done what I already knew before Castigliano's theorem. You know, that this is the general form. Now this would give me what the deflection of A would be due to this force in the x direction. But I don't want to find the deflection in the direction of this force, which is the tension force. I want to know the deflection in the direction of the total force. and this would not give me that information. Now I could easily just multiply P L over AE, which is kind of what I'm going to end up doing here. I have a P times L. When I do a dx, the integral, this is going to be from 0 to 15, and that's just an L. This dx is going to go from 0 to 15, and that's L. So P times L over AE. And then what is this 0.6? Well, if I only do this, I would get the deflection in this direction, but I want the component that actually affects that. So it would be another 0.6, like a sine of an angle between that triangle that I drew at the beginning, the 4, 3, 5. Okay, so again, I don't need to think about all of that, and I'm actually going to give just another example of that, because it would be way harder in that sense. So that's why we use Castigliano's theorem. So let's do the torque, which is the other example that I want to do. So it would still be 0 to 15. The torque is 0.8 F times 7, which is 5.6 F. So T is 5.6 F over JG times dt df, which is a 5.6, and the dx. So basically the same thing. When I do the integral, this is constant, so it's just from 0 to 15 of dx, basically multiplying by 15. And so basically I ended up doing torque times L, that 15, over JG, but I did get this value. So what is this value coming from? So I have the T, multiply the 15 length over the properties. That will give me what? An angle of twist, right? But I don't want the angle of twist. I actually want to know how much this end B went down due to that torque that caused an angle of twist. So maybe that thing made it rotated something like this. So that line is now over here because there's an angle of twist here going in the positive direction, and because there's another structure here, AB, connected to this point, A, that angle of twist is going to be represented as B going down. Okay, something like this. Okay, so if I was doing it without Castigliano's theorem and I'm just using the information about TLJG for my angle of twist, I would have had to multiply it by the distance of 7 inches. Okay, so if I do my angle of twist theta and I multiply by 7 inches, I would actually be calculating this ds, which is kind of what I want because that's where B is going to be. But also I don't want that would be going down. This would be B going almost all the way down, and I don't want that. I want that deflection of B in the direction of the force. So I would have to have 7 times that component, which would be 0.8 or 4 over 5. Oops, I was not recording that, sorry. So I'm going to repeat that. I have the angle of twist from this equation, but I would have to multiply it by the radius, in this case the length from A to B, to see how much B is going down. So if I multiply the angle times the radius, in this case 7, I would have my ds, which is the deflection of B, but B going down, not in the direction of the force. So I would still have to multiply it by a component 0.8 to find the component of that direction, of that deflection in the direction of the force F. Okay, so that's too complicated. Castigliano's theorem does all of that for me. Okay, so I don't need to do the regular equation that I knew here. I'm not gonna need any of this. I'm not gonna need any of this. Okay, and I just go back to this, and this would be 5.6 squared F over JG times L, in this case 15. Okay, all right, and so one more. We haven't done one that is a function of F of x or one of the variables. So let's do that. Let's go to a, b. Let's use one of these, which are a function of the variable. So let's do the first one. Mx would be here. So mx is trying to bend this in this direction, so this I expect it to go down. And I already have the my of z. What I know is that the farther away I am from b, the more the moment mx is, because I would be multiplying this force times this force times this distance. And that's why I'm also going to need the partial derivative with respect to f to come to my expression here and replace it. So basically what I just said is I have mx from here, from here, so 0.8 f times z. dm df would be 0.8 z over ie. Those are constant, they can go outside of the integral, times dz. This would be from 0 to 7. Okay, because I'm doing it from a to b, which is not to 15 but to 7 inches, and in the dz direction, which is where the axis, the central axis of the a b portion is. Okay, and now before I had stuff that was constant, so it could just go outside the integral, and then the integral would be 0 to 15 of dx, basically 15. But in this case, these are functions of z, so I will be needing to do the integral. So I know that ie is constant, but it comes out of the integral, and then 0 to 7 of 0.64, that's 0.8 times 0.8 z squared. And actually this force is also constant, it's the given force, so it's not dependent on z, dz. I would just do that integral. So I have f, I have the property of the material, I calculated I before, and then, well, 0.64 can also come out, and then it's from 0 to 7 of z squared dz, which would just be c cubed over 3, evaluated at 7 and 0. Okay, so basically 7 to the third over 3 times this constant, these constants, 4 f i e. Okay, so this is how I get a value. I would do that for the other 5 integrals that I have here, and when I add them up, they are already going to give me information about the deflection of b in the direction of the force. Okay, so just so that you can practice it, these values should be area equal to 0.1963 inches squared, I 3.068 times 10 to the minus 3 inches to the fourth, and this would just be double of that, so 6.136 times 10 to the minus 3 inches to the fourth. And the properties of the material will be 30 for the elastic modulus, 30 times 10 to the 6 for the elastic modulus, and 11.5 and 10 times 10 to the 6 for the shear modulus. Okay, and the total answer for delta B should be 0.279 inches. Okay, so you can work on these integrals and try to see if you come up with the same result.